on how it's made. Technical glass. Washing machines. Playing cards. And crossbows. A traffic intersection, a Hollywood movie set, the outside of an airplane. It's hard to imagine any common ground between them until you flip a switch, a light switch. Traffic lights, movie lights, and aircraft lights are all made of the same type of special glass. It's called technical glass. Borosilicate glass has a low thermal expansion and is very durable. It's used in high-temperature applications and when abrasion resistance is important. It begins with a mix of silica sand and chemicals called batch. Workers shovel the batch and recycled glass called cullet into a pot furnace where they melt for 2 days. A variety of colorants are added to make hundreds of different colors. Next, it's on to the molding process. Workers heat a ring and transfer it to the top of a mold. Then they twist and turn a stick called a punty to gather some melted glass and carefully string it in the mold. A plunger squeezes the molten gob into shape. The glass solidifies in seconds. This glass lens is used as a landing light cover on an aircraft. They extract it from the mold for a quick inspection, any imperfections, and it gets recycled. If the lens is acceptable, it's held in a forming device to finalize the shape. The burner maintains the proper temperature of the ring. Once formed, the lenses are cooled in an annealing oven, which relieves unwanted stress in the glass. This circular mold makes theatrical and landscape lighting. Again, a gob of molten glass is dropped in the mold and the plunger is depressed, forming the lens. Heat-resistant tongs enable workers to handle the hot lenses. Red and yellow lenses need a high-temperature anneal for the color to appear. This is called striking. Back on the molding line, special tools are used to ensure this aircraft lens maintains its shape. A quick spin on a light wheel illuminates any defects. After a trip through the annealing leer, the lenses are ready for further processing. The molding process for larger lenses can be more complicated. This large convex lens requires several gobs of molten glass, placed carefully on top of one another. The plunger enters into the molten glass, forming the lens. Deep ridges located in the plunger of the mold create the circular prisms on the glass lens. Within seconds, the lens is ready for extraction and inspection. Using heat-resistant mitts, workers scrutinize the glass from every angle, checking for small fractures or imperfections in the glass. Next, they inspect for flatness, using a paper-thin plastic feeler. If it slides underneath, the lens is warped and unacceptable. They check the glass thickness in many locations using a calibrated thickness gauge. Any major defects, and they discard the lens. In the factory's finishing shop, they use a diamond saw to slice away excess glass around the periphery. A special sanding belt is used to smooth the surface to perfection. Then, with a cloth buffing wheel, they polish the glass to a shine. At last, the final inspection. Using calipers, they measure the lens's ridged edge, called the flange, to make sure the dimensions are correct. Producing such a colorful assortment of technical glass takes a lot of work, but at least there's light at the end of the tunnel. In the days before electricity, doing laundry was just plain hard work. The first electric washing machines were little more than a bucket with a motor attached. Fully automatic machines came about in the 1960s. But with rising concern for the environment, there are new designs that need less water and electricity to get the dirty job done. Most washing machines contain a circular tub to hold the laundry, but this model has a unique feature: a hexagon-shaped tub made from panels of laser-cut perforated stainless steel. The operator separates the cut panels and places one on a bending machine called a press brake. It forces the panel against a die, bending the edge. The operator repositions the panel for the next bend, repeating this until the six-sided shape is complete. Then, an assembler attaches a hinged door to the tub's opening. That's where the laundry goes in. This inner tub is contained by another outer tub. To assemble it, a welder sets a stainless steel plate onto a welding fixture. Then he places the tub's main frame and slides in another steel plate to close it up. He clamps the tub firmly in place, then spot welds it on each side so the pieces hold together. Next, he takes the tub over to a machine called a seam welder. There, an electrode wheel travels all along the tub's edge, welding together the front and back panels to the main frame. There's still more welding to do with the use of a robotic welding arm to build the machine's 61 by 69 centimeter steel base. A concrete counterweight mounted on the outer tub's side prevents the machine from shaking too much when it's in operation. Next, an assembler attaches a pressure tube and a sump hose to draw the used water out of the machine. He seals both tubes with a watertight adhesive. Now he can install the suspension struts that support the outer tub, one at each corner of the base. A single electric motor powers the whole machine. It's set on the machine's underside, on an adjustable pivot shaft. With the motor in place, assemblers now turn over the completed outer tub and lower it into position on its base. They connect the support struts on all four sides and then push the tub to make sure the struts align properly and keep the machine balanced. Next, the inner tub is set into the outer tub. Workers insert a stainless steel shaft right through both tubs. A strip of watertight foam is set all along the outer tub's perimeter to seal it before workers install a plastic bezel that keeps water from splashing out of the machine. Next, assemblers install the drive pulley onto the shaft that supports the inner tub. A drive belt connects the motor to the pulley, which rotates the shaft and the inner tub that it supports. Now they slide a stainless steel outer cabinet onto the base that covers the tubs. It contains a control board, the brain of the washing machine. The assembler sets the lid into place and the machine is complete. The control board wiring is located on the underside of the lid. That's also where the valves that dispense detergent, bleach, and softener are. Before it leaves the plant, a member of the quality control team tests it out with a load of soiled laundry. According to the manufacturers, the unique shape of the inner tub is the key to making this a lean, green washing machine that requires less water, less detergent, and less energy to get the job done. There's been a lot of water under the bridge since the days of those first machines. They've sure come a long way. The playing card traces its roots back more than 1,100 years to 9th century China. Since then, generations young and old lay down their true colors in a variety of games, each as unique as the traditional 52-card deck and as timeless as the 4 famous suits. Whatever the hand, a winning combination of technical features makes these playing cards durable and cheater-proof. Industrial humidifiers control the moisture level of the cardstock. This prevents the cardboard from drying out and warping. Technicians regularly monitor the cardboard's temperature and humidity by inserting a flat probe 10 centimeters from the top of the 3,000-sheet stack. Cardstock arrives from the paper mill ready-made, 2 layers of cardboard bonded with colored glue. This construction makes the playing cards impossible to see through. Before making printing plates, a technician checks the artwork for the deck, then prints out a low-resolution sample to confirm the sequence and layout are correct. There's absolutely no room for error, so she carefully double-checks every card for suit, sequence, color, and layout. A signature on this sticker confirms these cards are good for print. The next step is to make a digital proof. This printer's internal laser heat transfers dots of colored foils onto a clear film. These dots perfectly reproduce the content and color of each card. Next, a laminating machine bonds the exposed films onto a sheet of the same cardboard used to make the cards. This produces a printed proof showing exactly what the finished playing cards will look like. Here, graphic artists adapt hand drawings of the face cards, adding color and a touch of regal class wherever needed. The next step is to make the printing plates. A computer-guided laser etches the design into the polymer surface of the printing plate. Entirely automated, this machine produces 30 plates an hour. To set up for a print run, workers pour several cans of thick cyan ink into the ink duct. The 3 other colors, same setup. When the printing press gets rolling, each fountain will disperse ink evenly via 16 rollers. Feeders transport the cardboard sheets one by one into the press. Each printing plate is mounted on a rotating drum. Rollers transfer the ink onto the plate, which then transfer onto a rubber blanket, which presses against the passing cardboard as it moves through the press. At the end of the machine, the printed sheet is flattened and stacked. They feed the same sheets back through the press, this time upside down. The sheets now move through a cutting machine called the combi, where rotating blades divide the sheets into columns, then into individual cards. The cards get grouped into decks. Then the deck heads into what they call the cornering station. A die descends and in one fell swoop cuts off all 4 corners. Next, a robotic arm nudges each deck onto a conveyor destined for the cello wrapper. Grippers pull a cellophane reel downwards while a knife then cuts the film. A heated bar descends and seals the film, which forms an envelope. With a simple pull, the red tear strip removes the wrapper. The traditional English deck is the international standard for games such as poker. But there are many more types of playing cards. This set of Spanish cards, for example, has no numbers, just symbols. Whether at the casino blackjack table or the kitchen table, playing cards are the real deal. A crossbow is a modern bow and arrow that you shoot like a rifle. It's popular for both target shooting and hunting. With a rifle, you can shoot from 180 meters away. But using a crossbow is more of a challenge. You have to be at least 4 times closer to your target. A crossbow consists of the bow and the stock. The bow shoots the arrow while the stock houses the trigger and the aiming scope. A plate of fiberglass is the starting point for the bow's limbs, the 2 curved arms that pull back and release to shoot the arrow. A vacuum holds the plate steady as a computer-guided grinder does some initial shaping. Workers measure the plate with micrometers to ensure it meets strict specifications. This is a special type of fiberglass. The fibers all run in the same direction, meaning they can bend repeatedly without weakening over time. Workers mount the plate on a computer-guided cutter. It carves out the limbs with a high-pressure water jet, the most precise way to slice fiberglass. Each plate yields 4 limbs, 2 bows worth. The severed fibers make their surface rough, so a little polishing is in order. The limbs go into a vibrating tub filled with ceramic stones that rub against the limbs, wearing down the coarse fibers. Now the limbs are ready for decoration. The design is printed on plastic film. This machine uses heat and pressure to transfer the design. The next bow component is called the riser. They machine it out of aluminum, then jazz it up with an ink transfer. To assemble the bow, they bolt a limb to each side of the riser. It acts as a spacer, separating the limbs so that the arrow can pass between them when you shoot. The riser and limbs go into a press, which applies more than 300 kilograms of pressure, bending the limbs into an arc. Next, workers mount a set of aluminum pulleys on each limb tip. These are called compound cams. Next, the yoke. A yoke is a string with a loop on each end. They anchor one loop to one side of the limb tip, pass the other end through a loop on a steel cable, then anchor it to the other side. This forms a Y shape that distributes pressure on the limb evenly. They repeat the same process with a second yoke on the other limb. Now for the bowstring. On each limb, they attach the bowstring end to one side of the cam. Then they anchor the cable, coming from the yoke, to the other side. Next, 2 rubber silencers go onto the bowstring. When you shoot, these silencers absorb the string's vibration, reducing the sound. These components make up what's known as a compound bow. This design enables the bowstring to propel the arrow farther. Now the bow is finished and ready for testing. This scale measures how much strength it takes to draw the bow. Elsewhere, the stock is coming together. First, the trigger mechanism. It undergoes extensive testing in a specially designed device that applies air pressure to simulate the bowstring tension. They pull the trigger 6 times to ensure it fires properly. Then they apply the safety catch, and with a strap to get maximum strength, they pull some more. This makes absolutely sure the trigger won't fire accidentally in the safety position. After attaching a connecting rod that fits into the bow's riser, they install the trigger in the barrel. Then they bolt these components into the stock housing. They attach a bridge and rail on which the scope will mount. Now they test the trigger again to check the installation. Connecting the crossbow's two sections is simple. You insert the stock's rod into a slot in the riser and tighten a mounting bolt. Then you attach a foot stirrup. To cock the bow, you stand the crossbow on the ground, put your foot in the stirrup, and pull the bowstring upward until it locks into the trigger mechanism. Then you pick up the crossbow, aim, and fire.